All right, so I'm going to go shit. We're going to continue the example. Remember, we're still working through the attention mechanism, but we're just adding this concept of masks, right? Again, all that we had said in attention still applies. The only thing is I've added this thing of masks where in the diagonal, the numbers for 1, above the diagonal, there's 0, and below the diagonal, they're 1, right? And the intuition is, just like in BERTs, we randomly blank out some words so that the model learns to fill in the blank. Here, in the attention mechanism, we don't want it to look at all the words. So one sentence, needs to learn to predict the words. So it's, like the next word or whatever. So it only looks at wherever you are, the words before you. Okay, that's essentially. So that's why we do this. Now, mechanically, we've done all these steps, right? So we created a mask. Oh, did I not? Sorry. All right, great. So I'm just repeating what we had done before. We had created this mask over here. Then I created randomly an attention scores. Remember, this is the result of KQ. So in this case, I'm using 10 by 10. And I can apply like an if statement, right? Because I want to do an operation. Okay, so here is the moment when I apply the mask to the attention score. So I have a matrix, attention scores, and another one mask, and I'm going to apply it. So you can see that I'm using this trick called for a tensor has this feature called a masked fill. So I can apply that, and I'm going to say whenever the values are 0, change that 0 into a minus infinity. And you'll see why that's done. It's just a trick. Okay? But essentially, you can still think of it as being 0, and everything that is, I want to just leave as is, because those are the weights that we want, the values that should be paid attention to. All right, so I ran this one, and now you can see this is kind of what the attention would look like after I have performed a K times Q. All right, here you would have values that were computed, and these are just minus, zeros or minus infinity. The point is it ignores those connections. So for instance, to go back to the logic, this 0.39, if it was an actual weight, it would be emphasizing that there's a connection between this and that. Okay, that word. So bank and river, and boom, now it knows the context of bank. It's the Sandy thing and not the financial institution. So that's what is happening in the code there. So now I'm going to continue. And what are these negative infinities? So we've looked at it already. These values. We apply a softmax to this, a softmax function. Okay, and when we apply the softmax to the attention, what happens is I haven't defined F, so let me. There's a import function like that. Yeah, this one is at the top. So I need that feature there. Okay, so I apply the softmax to it. So this is a step that happens in the model. I hadn't included this before, but now I'm including it of applying the softmax. Okay, I just did that. And now if you notice, when I look at that same attention matrix again, the values are no longer minus infinities. They are what? Zeros. Do you see that? So why? Because we actually want to apply the softmax. But the problem is if we just had zeros there, the softmax didn't quite work. Do you see that? So we had to do a trick where when we put minus infinities in there, then the softmax turns that into zeros. Okay. Yeah. So what we wanted to, what we want is we have this attention scores, right? We have it, I guess. Let me do this. Hold on. So I have this. So you see that, so I perform this operation, right? And I would get this all zeros here. But later I want to apply a softmax to this function. When I apply a softmax to this, it doesn't give me the results that I need. Okay? So you have to do a trick. You apply this operation where instead of zeros, you change these to minus infinity. The definition of softmax is that it's going to turn minus infinities into zeros. Okay? So it's a trick. It's not something that we wanted to do, but it had to be done for us to have the right information in there. Okay, so I do then, you can see the right step is to make these into minus infinity. We intentionally do that. But that you can think of them still as zero. Because in the next step, we want to apply a softmax to the attention scores. And once we do that, and we look at the values, the softmax itself makes them zero for us. So that's why we have. Yeah, go ahead, please. That's right. That's right. Why? I love the observation you made. What do these represent? They're called logits. By the way, you'll see this term a lot. Logits. What is a logit? Logit is just these values. Values that are in transition in these operations, and they're going to become like probabilities. We refer to them as logits. So these are logits. These are logits. But here you just said they're no longer negative. They have certain properties, right? And what the softmax usually is trying to convert something into more of a probability distribution. And so probabilities are, what? 0 or 1, right? Or something in between. If you have a distribution of probabilities of 3 classes, you would want those to add up to 1 also. Do you see that? So that's one of the 110 problems that I gave you in the problem set, right? What the softmax. Do you guys understand that, guys? Yeah, all right, great. So you can see it, right? How many values are here that were not 0? Just 1. What does that value add up to? 1. Well, 1, right? Okay. How many values do I have here that are not 0? Just these 2. Once I softmax them, do you notice something interesting? They add up to 1. Let's go over here. There were 3 values there. They add up to 1. You see my point, right? So I don't have to go all the way to the end. Softmax is like an amazing function, okay? It's an amazing function, and we use that a lot. We want to use that a lot before, I just had random, these were not adding up to 1. Do you see that? So we force the transformer in the attention mechanism. See what an amazing thing this is, right? We take the x's, but we also convert them because we want to give it that chance. We also compress them. We also very elegantly with this little triangular mask tell it, don't look ahead. And also, when you predict your values, when you when you calculate your probabilities, make sure that they follow a nice probability distribution that adds up to 1. And all of that is achieved in this little attention mechanism. It's very prominent, right? And that's why it was in the Vaswani paper as a very elegant solution. So we did this over here. And so now, if you think about it in the context of, the robbers, so let's go back to the whiteboard. We're going to think about this in the context of the bank, the word bank. So it's saying, the bank of the river, the bank of the river, right? So obviously the words that we care about here are bank and bank of the river. So this river. But we know also that there's a value here, there's a value there, there's a value there, and there's a river and river, of course, are related to each other. Do you see that? So it's not only saying that I pay attention, because it could say, think about this, right? It could say the bank of the river, I'm going to add a word in here, the wet bank of the river. So now there's a word here in the middle, right? Yeah, so think about this one. Okay. So I looked at bank. How am I doing? The wet bank of the river. Yeah, so here, right? So it would look at that here. So it's essentially, it does this to river here. And it could say that this one and this one, maybe this is 0.6 and this is 0.5. Do you see that? So both of these weights are highlighted as important, right? Do you see this? Like these scores are highlighted as important. But the problem is they don't actually reflect a true probability distribution, and they're kind of like close to each other. So by doing the softmax, what you're essentially doing is like forcing it to be a little bit more distinctive. All right. So now if I wanted to fix this, when I apply softmax, maybe this one becomes 0.20, this one becomes 0.40, and the other ones get values that together, when you add them up, equal 1. So although the difference might seem subtle, this is really important. The model will be better almost always when the data is like this, because it's more precise in the differentiation. Do you see that, guys? So that's what it's doing. It's creating these like probability distributions of the attention score. Yeah, go ahead. Mm-hmm. In an attention, you always apply the softmax in an attention. Yeah. Do you mean after you leave this and you go to another layer? Yeah, when you finish this is just a tensor. And what do? Remember, you let's call this one way. So what do we do then? We have V matrix multiplication way. Softmax produces values. Once the values are produced, forget about softmax. Softmax did its job, right? Converted whatever an input was into another output. You have values here, right? And then now forget about softmax is done. You just have a tensor. And then that tensor is way, which will get matrix multiplied with V. There is another softmax I can tell you at the very end of the transformer. So there will be other layers that might require a softmax. Some places, but essentially here, what's important is to understand you actually caught this so well, right? So he looked at it and said, hey, by the way, I noticed that the values initially were negative and did not add up to 1, and now they add up to 1 and they're positive. You see what I'm saying? So that is essentially what you do. So, just to make it tighter, it's like a tightening of the precision. Okay? Any other questions, guys? All right, so let's move on then. So we've done this mechanism here, right? And now we can see it. So we'll just repeat it again one more time to get a sense of how it works. So I'm going to do it even smaller because that's really it. After that, what you have is the V's, the V multiplied with way. Okay, so let's assume a smaller one. So this one is the random attention scores. This is just 6 by 6, so assume a sentence of 6. Okay? Then I'm going to, we're going to look at the value. Just a whole bunch of negatives, right? So here's a good example. Imagine these were positive. 0.71 plus 0.72 does not add up to 1. Do you see that? And so that's a logit. But you always, when you're selecting over several classes, which we are here in a sense, right? Because one word, bank, is selecting over what? Wet and river. Which one is more important? It's a selection, a type of a classification. You could have a wet bank, right? But the river word is more likely to be tied with, it could be that the bank is next to the river, but it's more like the bank of the river, the sandy bank of the river, something like that. Okay, so although we have these as 0.71 initially, we want to use softmax to make them a little bit tighter. And so then, but we also apply the mask, right? Now that infinity thing, if it confuses you, just think of it as it's necessary because we need softmax, but with a 0, softmax was messed up. And so we needed to correct that. And so I run this one over here. Now I have it, I've applied the mask. So the top part should be gone. Okay, the top part should be gone. Whoops, I'm going to close this. The size, it's the same. So I run that, but it's minus infinities, right? Because I'm going to apply the softmax and I need that. So now let me do this. And I'm going to do, I apply the softmax. And now we look at the values. Well, I can make it bigger. Do you guys see that? Yeah? Let's try one more thing. I'm kind of curious about something. I've never done this, but you guys have grilled me so much today. Let's take a look at this. So 0 was the original value, correct? Okay. So let's try this. I'm just curious. I've never run this before. Okay. All right. So 1.4 and 0.89. That if they were positive, they would not add up to 1. Okay. So I need a softmax. Okay, this is x 0, right? So I remove that infinity. You see, that's all I'm doing. I'm removing the infinity. Now I'm going to apply the softmax. So that should be applied. Yeah, there it is. See that? Applying the softmax to the whole matrix when the values at the top were 0 messes up everything. It should ignore them. And instead, what did it do? Yeah, so it made the series, it's actually like including them, right? So this will probably add up to 1. This whole thing will probably add up to 1 if you do it. But that's not what you want, right? What you want is for the top ones to be ignored, and so we apply the infinity to it. Does that make sense, guys? What was that? Minus inf. Oh, this. I'll copy this. Oops. Yeah, so now notice, it's accounting for all of it. We don't want that. Made that like that. See it, they're now 0, always 0. So why is this important? If we didn't do it like that, if we had it like we had it before, what would happen when the model's training? The weights would shift or be nudged in one direction or the other to produce values on here, right? It would be trying these values. It would be optimizing towards that goal. But because we always make these top ones 0, there's no signal. There's no signal there. So the weights then don't do anything there. They only do things in this bottom part. Here, so what you want is change, right? What's the point of training an LLM with all the text in the world for 3 months if these values, every iteration, are always 0? You see that? There's nothing happened. So the only place where things change is in this bottom part. So the weights are changing constantly in the LLM, and this is changing until eventually this is meaningful and helpful for the prediction. And then you have a nice set of weights. Got it? Any questions? That's all. That's it. So that's the attention mechanism. Keep in mind, it's busy, right? It's very busy. There's softmax, there's the trill mask, there's K and Q, but you're essentially but it's very important for that context. So Bank of the River versus Bank of the financial institution, because remember, the key is that the embedding of bank will be different if it's one or the other. And that's how it knows what it's, how it understands what it's looking at. Otherwise, your answers would be, sometimes you're asking it a question about a financial institution, would start talking about a river because it doesn't know, right? So it needs to understand that. All right, so that essentially is it as far as masks. That's what's so nice about the GPT. There's only this mask and nothing else. Okay? And it's like I said, it's like a constant. All right, so let's go back to the document. I believe this one is done here. Okay? And then we did token embeddings and positional encoding last week, correct? Guys, all right. So we've covered this one. So great. So I think we have enough time to finish. So now what I'm going to look at is tick token. So in your homework number 2, I have not included tick token in the Huck Finn code I gave you because I intentionally left that for you guys to do. So you'll have to integrate tick token into that code. But tick token is pretty important. Let's continue down here. So I'm going to do this. So now I'm done with this script. So this script is done. And I'm done with this one. I'm done with this one. So what's next is this one here, background. And you can see I import tick token. So if you don't have it, you can just do pip install tick token, and you should have that library. So let me import it. So what is the point of tick token? So tick token is how you convert text to integers, to numbers. So the transformer cannot take in actual text. That doesn't work. We know that there's actually the IDs are going to be converted into embeddings of size 512 or whatever it is. But before that, if you remember in a lot of my previous examples, I created a lot of integers, right? Randomly. So if you remember in this script here, so in this script here, when we did the embeddings, I don't know if you guys remember, but I created these integers here. Do you remember? And I just did it randomly. Well, obviously, we wouldn't do it randomly, in reality. Instead, we're going to start with a set of sentences, a batch of sentences, and we want to convert it into this, okay, meaningfully. So that's where tick token comes in. So I'm going to go ahead and do that and show you guys. And this is really important for you guys to do your homework too. So I'm going to click on background, and it should be pretty straightforward. So I'm going to go here. So the first thing I'm going to do is I'm not going to train a text to IDs, methodology or anything like that, because that would require that I would take all of the text, run it through an algorithm called BPE, and then BPE would create this vocabulary for me, right, of tokens to use. Instead, what you can do is just take one that has already been created. So for instance, when they trained GPT-2, right, imagine that GPT-2 was trained with, 1 million books and 1 million websites from the web, right? So they took that data set, they applied BPE to it, and BPE produced 50,000 subwords, okay, that were the most frequent in that. Now, the token, subwords or tokens are not words, not all the time. So they're more like syllables. I think I've mentioned this. So think of, ing, for instance, like happening, right? Calling, right? So ing in the end, that little ing is like a subword because it's meaningful. So for instance, I could say, I can see Gen Zers say something like, I'm going to make something up, but let's say, hey, I was iPhoning with my friends. All of you understand what I mean by that. Even though you've never heard it, it makes no sense, right? But yet, I put iPhone and ing, and I created a new word, iPhoning, and then you understand that it's like the act of using an iPhone or something like that. Yeah, go ahead.
So unlike random numbers, like researchers at some point sat down and decided ing was 174.
No.
Okay.
Instead, an algorithm called BPE decided.
But it was not random. It was
It's not random. Yeah. So the algorithm BPE looks at, that's why I said, so you take BPE and it takes all the books in the world and all the websites in the world, and it runs through them. And it then crunches numbers, and it says, okay, I'm going to break. Imagine it takes words and it breaks them into parts. And one of those is ing, and it found that appeared in a lot of words. So it said, this I think is an important thing. It's not a syllable because I'm calculating this with statistics. So I'm going to call it a subword. But I'm going to identify that in my top 200,000, ing is a term, and also it's ranked by importance. So I'm actually going to say that this is like in the top 1,000. Maybe it's ID number 998. Yes. So whatever I could be ID number 1. Exactly right. Exactly right. Cat, which is fairly common in a lot of things, could be like 17. But xylophone might be like 5,000 or 50,000 or something like that. Do you guys see that? And of course, of these 200,000 subwords, you don't actually have to use all of them. You just use the most frequent. As it turns out, I think a lot of the models have used about 50,000 because, if you had just, happy, right? So there's happy, happier, happiest, happiness, so many. So what you do is you'd have to have all those words. It would make for a very large vocabulary, or you split it into this and the model can produce its own words. So yes, right? So that yes appears in other words. So then it can create happiest, iPhoneiest, whatever that means. Yeah, go ahead. That's a good, I don't know what the BPE does exactly. So there could be a happiest. What I could say is the happiest might be 45,000 ID. And yes might be like 2,000. And hap with two P's maybe is like, I don't know, 1,300. Yes, go ahead. No, go ahead. It can do it with every language because this is an algorithm. BPE is not like rules of English and syntax and grammar. It's a pure math thing. Yeah. So you give it any language of text, yeah, it'll be able to do the exact same thing. Exactly right. In fact, their models, Roberta XLM, was trained on like 100 languages. Yeah, you can give it, this is common, right? You can give it, you have all the internet in English and all the internet in Spanish and all the internet, in whatever, right? So in Russian and you give it all at once and it can create these vocabularies if it wants to. And actually there may be common patterns, which is quite interesting across languages. In the way?
As long as it's in the internet, it's like little data still want to recognize breakdown.
Yeah, so the goal of BP is just to produce a vocabulary of subwords, nothing else. It's nothing to do with the LLM. It's so go to whiteboard here. So there's actually two passes. Yeah, there's two passes to train an LLM, right? So pass 1 and then pass 2. Everything I have been doing has been this part, right? So I created literally lists of random IDs because I didn't have this part yet. But pass 1 is essentially you take all the data, right? This is all the data, and you're going to feed it into some algorithm. I think the best one currently is BPE. So it goes in here, and this looks at everything and, ing and whatever, and it produces essentially a vocabulary, like a dictionary. So vocab, where it's going to be ID 1, 2, 3, 5 to the actual word. So you said I, and this could be ing, and this is whatever, hap. And then usually people just select the top 50,000 because they believe that with that they can compose many, many other words. Do you see that? So once that's done, I'm going to use a different color here. The same, remember, this is all the data, right? All the text, the books, Huckleberry Finn, etc., was fed into BPE. BPE just produces the vocabulary. But now you once again give all the data to the LLM or the GPT. But the LLM needs these IDs, right? But what we have is we have text. So we have to use this vocabulary to take this text and convert it into the IDs that will go in. Do you guys understand? Does that make sense for everyone? Yeah? All right, perfect. All right, so so there's two passes. So now what I'm showing you is how we can do this. So, I'm not gonna run BP because first of all, I need a lot of data, right, to produce the vocabulary. Instead, we just, borrow from the work of other people. So other people, when they were training GPT-2, they gave it all the text, ran it through BPE, and created this vocabulary. So tick token allows me to grab, and I wanted to use a different vocabularies from different things like GPT-2, GPT-3, Llama 3.2, whatever it is. And that should be perfectly fine because think about it. For Llama 3, you still probably selected ing. That's, very useful, right, in language. Or hap or whatever it is, I. It's still the same language. All right, so we have this. So now we can try tick token. So we can try tick token. All right. And see what I'm talking about. So we've got the, I haven't imported it. So now I'm going to do tick token, get encoding, GPT-2. There you are. I just grabbed the vocabulary and now I give it a string and it's going to give me the sequence of IDs. But this is critical, okay? And we will see this later. So here's an example. So this one is, hello, do you like tea? Okay, that's the string. Like it would be coming from your text data. And we need to convert it into integers. So we call this a tokenizer. And I'm going to apply the encoding part. So essentially, I take the text and boom, there's my integers. That's it. That's the magic. And this is really nice. When I do Huck Finn, my vocabulary will actually just be letters. Just every letter is going to be a token. And I can generate words like that, right? But we will see that that's not the best way of doing things. It's better to have ing as a subword than ing. The predictions like that can be ing. You see what I'm saying? Because why not? But by having ing, we're forcing the model. It's either ing or nothing. And that's much better at producing words. So it's a nice experiment when you guys do your homework too. Try it with the characters alone and with tick token. BPE is so crucial to the success of LLMs. Like LLMs or ChatGPT. Yeah, please. Yes, exactly. These IDs, right. So I can look up one of them, for instance, and I should get one of the things in here. For every time that you see the 8887? Yes, that's it set in stone. Yes, I'm using the vocabulary of GPT-2 because I can do it because what I will do is I will take my text, and convert it into this sequence of integers following that rule, go into the transformer. The transformer produces a set of integers, And that set of integers then can be mapped back. You see, integers go in, integers go out. And then you map strings to integers and integers to strings using that GPT-2 vocabulary. So that's why it works. Yeah, perfect. All right, guys. So we have some IDs here. So now we can play with it a little bit. Let's do, here I have two sentences. You know, hello morning, do you like tea? And I am good, thank you. Okay. So now I can tokenize these into integers. And you can see that here I have integers, right? And there they are. I have integers too. Oh, I deleted integers 2. And you see is the other sequence of IDs. Got it? Any questions? All right, pretty easy, right? And then here we can concatenate them. For instance, I can create a list. So let's call it integers. And I'm just going to give it one. So let's see, I'm going to give it 2854. Whoops. Oh, why did it give me performance? Because it's 2584, not it's 2584 KY. Why KY? KY there. Why did it create that? I don't know. That's BPE, right? So BPE creates its vocabulary called subwords. Got it, guys? So here I can encode and decode. If I gave it this whole list, for instance, I should be able to get the sentence back. Yeah, I am good, thank you. So what does the transformer do? The transformer predicts a sequence of integers given a sequence of integers. Do you see that? So we give it this sequence of integers, goes in, it'll predict a sequence of integers, then we map that out to whatever string it is based on our vocabulary. Good. One is double. Oh, okay. Yeah, good. Yeah. So you can play with it, but there you are. So you can see tick tokens pretty easy. Next Thursday for you guys, I will do the Huck Finn. And with Huck Finn, we're not going to use GPT-2. Instead, we're going to data wrangle. And so I'm going to set a vocabulary of just letters. So it's going to be A is going to be a subword, B is going to be a subword, and so on. And we'll see how this whole process works. But for your homework, try both and convince yourself that this is much better. Okay? So now let's go ahead. I think in the time that we have left, we have enough time to wrap up everything, right? So believe it or not, maybe it was a rough going here, but we've made it to the end. So that in the sense that we've looked at all the operations. So all the tensor operations of the GPT have now been covered. And so now I can put everything together in the baby GPT. And that's just so that we can see a super compressed version before we look at the complete full-on version next Thursday. And that wraps up everything. And so some simplifications, right? So this GPT, and actually for this one, I'm going to use just very quickly my notes, because I want to show you something. So in my notes, have this chart, right? So this is, remember, the full transformer, but we're only focusing on the GPT part, the decoder. So this blue line, get rid of it. Throw it away, and then they're disconnected. So what have we covered? This is the full-on GPT. So we'll start here, n by 40, right? Batch and sequence of 40, where the values are IDs, right? We've done this. It goes in, we do the positional encoding, right? And everything, right? We've covered that. And then we will go into just one of these. We will go into a decoder layer, and that's it. Notice here, there's actually 6 decoder layers, but they're exactly the same. We just, tensor of n by 40 by 512 goes in, n by 40 by 512 comes out, so that can go into the next one. So why here in this example, the baby GPT, I just decided to get rid of these 6, and I'm only doing 1. Okay? Another simplification is that this decoder layer has an attention. But in the attention I'm going to do, instead of doing 8 heads in parallel, I'm only doing 1. Okay? Later next week, we will do the full-on 8 in parallel. Okay? And then, of course, once I come out of this decoder layer, I'm going to go through a linear layer and finally map to the vocabulary. Okay? So that's essentially what's going on here. So I think one of these graphs shows a decoder layer inside. Yeah, this one. So notice, N40 by 512 goes in, N40 by 512 comes out. Inside each one of those blocks, there's a multi-head attention followed by a fully connected layer. I showed both of these independently. Just again, as I said, it's not a multi-head, it is a single head. And we'll look at that. So no concat is happening. We'll look at that in the full. All right, so now we are ready to finish this up. And you guys can, go play with it. But all I'm doing still is just the architecture from input to output, right? We haven't trained it or anything. Training will also happen next week when we will train it with the adventures of Huckleberry Finn. So now the code that we need for this is the one in here called baby transformer. Okay, so this is the one, the last one. Okay, so I'm going to, as you can see, the code is, that's it. Look at how short it is, right? Pretty short. And, we can go through this fairly fast because we already understand all these operations, essentially. So let me go ahead and get started. I'm going to grab the libraries just so I don't miss anything. All right, so I have all my functions in here. Then I'm going to have some parameters that I'm going to define. So what are these? So I have batch size. Instead of 32, for visualization purposes, I'm only going to have 2. Remember, that's 2 sentences. Sequence length is 10 instead of 40. Vocab size is going to be 1,000 instead of 50,000. The embedding dimension, that 512 and 40 by 512, here it's 64. Okay? And the final one, FFD 128. If you remember, I did one where I went from 512 to 2048 and 2048 back to 512. Do you remember that step? That's what this is. So this 128. Okay? So, okay, I'm doing that one. This is the full on from beginning to end. So here I'm going to not use tick token. Instead, I'm just going to randomly create my 2 sentences of integers. There they are. Random. But this is the input. If you had text, tick token produces this. Okay? All right. Notice that the sizes have to be 10. And on all of them, if the sentence is shorter than that, you would pad it or something like that. Okay, so I've created that one. Now, you should remember that we did this, right? We did this last week. We created the token embedding and the positional embedding. right? So if you don't remember, go back to those videos. The trick was that this is a matrix 1000 by 64, and this one was sequence length by 64. So it would have been what? 10 by 64. Very good, because we have 10 positions in the sentence. Perfect. But they're both 64, so they can be added together, right? And that's really what matters. Okay, perfect. So I instantiate these using the NN embedding. This should be familiar to you now because we covered it. Okay, perfect. So now I'm going to take both of these. All right, so if you remember, for the semantic embedding, all we had to do was take the integers, these guys over here, run them through the token embedding, this, to produce this. So instead of 2 by 10, it becomes 210 by 64. Remember, now every element is not an integer, is a vector of whatever, 512 or 64. For the positional encoding, we do the same, but with positions, right? So if you remember, so we just apply, well, we can look at positions. I've already done this, but if you remember it's just 0, 1, 2, 3, 4, 5, 6, 7, right? The position, and then that gets embedded or encoded. So we run positions through this to produce X position. Remember that both have the same dimension, which is something that some of you were like, how is that possible, right? And we add them together. So to produce your input. If you look over here, we take X token, which is 2 by 10 by 64, plus X position, which is also 2 by 10 by 64. They add up perfectly. And the tensor that we get is 2 by 10 by 64. Okay? All right, so we have now X, which is we're currently there. That's our tensor up in the model. We're still essentially, so currently we are here. This is where we are in this graph. Currently, that's where your X is. It's about to go into the first decoder layer. So, but before it goes in there, what do? We create our QKV. Now notice that I'm creating it a little bit different this time, right? I'm using NN linear. NN linear is a construct that allows me to, all at once create the weights, the biases, and everything. So essentially, if you remember how I would create WQ, right, in the example, and then I create BQ, and then, come on. And then I would do what? I would take X, matrix multiplication, WQ plus BQ, and that would produce my uppercase Q. Remember all of that we did last week? I had to, create one, then the other one, then do the matrix multiplication all, explicitly. All of that can be done just by doing NN linear. Okay, so that's the beauty. So an NN linear inside is it's code wrapping. It's pardon? Yeah, it's like a function or a class, object oriented, but it's essentially a whole bunch of lines of encapsulation. That's what I was thinking about. So a lot of machine learning is encapsulation. Hugging Face, the very powerful library Hugging Face, it's still PyTorch under the hood, except that they've taken 20 lines of code and they create a one function that includes all of them. So and then your code becomes less like verbose. And so it's encapsulation. So what I did is imagine I encapsulated all of those lines of code into NN linear. And you should convince yourself that that's what's happening there. So this equation is happening inside, and the objects WQ and BQ exist, but inside as a class. So I'm doing all of that. And so now I create my these are my Q, K, and V. I just used a different terminology by using this and then embedding. If you see, it's just, in this case, 64 to 64, okay? Before for us was 512 to 64. Remember, because we were compressing it a little bit, but in this baby GPT, I'm not doing that. All right, so that's done. That's the instantiation of it. So not actually like applying it yet. So that's the definition of it, I should say, sorry. So now that I've defined WQ, they're like a function. So notice what I do. I run X through all three, and guess what? They become my familiar QKV. Exactly what I did before. Everyone with me, guys? Confusion? All good? All right. So I got my KQV right, exactly as before. Now I proceed to the next step, which is the dot product, the multiplication, the matrix multiplication. So notice here, first of all here, right? You should convince yourself that this is Q times K, right? That's the matrix multiplication that we've talked about, Q times K, many times. The transpose, I already showed an example. It was just like flipping for the dimensions to be correct. And there is this parameter that I haven't talked about. It's a normalization. Imagine taking that matrix divided by 64. That's all it is. It's a normalization. But you can ignore it if it confuses you. And that produces my attention scores. Notice I'm not applying the mask here, just I wanted to keep it short, and that would have added several lines of code. But I showed you that here we would apply the mask. I did include the softmax though. So remember, the attention scores would then be masked, right? And then after that, that would go into softmax, which we've discussed. But notice that's essentially that process. Okay? And notice there it is, 2 by 10 by 10, right? You all agree? It's that attention scores. Then I apply my V, right? Which we've talked about several times. So I take my attention weights, which is this one, 210 by 10, matrix multiplied with V, and I get again my 210 by 64. Do you guys see that? It's the exact, I'm just putting everything together in the flow of it. Once that's done, we're almost there. We're like there. So we have now come out of one of these decoder layers. Do you see that? Well, outside of the attention, we're still in here. What comes next? A feed forward. So let's take a look at that. So I'm going to take this one. And this is the example of me going from 512 to 248 and then 248 back to 512 and giving it that room. That's this. If you notice, this is 64 to 128, 128 to 64. So that's just a normal feed forward layer. And we're almost done, guys. We're almost done. Just want to finish this. And then here, then, we apply it. So if you notice the attention output, which is this one here, right, it's going to go through these layers here. So if you notice, we do the attention goes first into FF1, this one. So think of it as going from 64 to 128. We apply a ReLU activation function, which essentially removes any negatives. That's all it does. And then that tensor goes into FF2, which is this guy over here. And what does that do? The 128 goes back to 64. Everyone with me on that? Yeah, so the feed forward, these two layers, right? The tensor is currently 210 by 64. All this does is it transforms it or projects it into 210 by 128. Do you see that? And then that 210 by 128 goes into a ReLU function. That's actually, believe it or not, what provides nonlinearities. That's what gives a lot of power to neural networks. And so it converts the numbers there. Any negatives, gone. And they become what? Zero, the hockey stick, right? Any positives remain as they were. That's all that happens in the values themselves. And then that tensor is what? 210 by 128 goes into FF2. What does FF2 do? Converts the tensor 210, 128 back to 210, 64. Do you see that? So goals there to give it a little bit more room and actually run it through a ReLU, which actually is a nonlinearity, and then back down to 210 by 64. Okay? Questions? ReLU is the rectified linear unit. It's a function that takes any tensor, right? The values in a tensor, and if they're negative, they're made into a zero. If they are positive, they are left as is. That's it. We can see that a little bit later. But yeah, that's all it does. Got it? All right. And then once the tensor, now it's back to being 210 by 64. Hopefully you agree with that. And what's left? Well, that's not very useful because that's an embedding. Remember what I was saying in the encoder? It comes out as an embedding. 210 by 64 does not mean anything to us. It means something to the transformer, no doubt. What do we need? We need to make it into IDs again, integers. So now it needs to go from 210 by 64 to 210 by vocabulary size, whatever it is. Because that embedding of 64 now gets mapped to a softmaxed vector of all the possible words that it should predict. So that's this. So now if you notice, I just came out of this linear layer because I skipped all of these. And now the tensor is n by 40 by vocab size. In my example, I'm using 1,000. So I'll prove to you that that happens just by doing a matrix multiplication. So notice here, I'm going to create a new layer, the final layer. Notice there it is, n in linear, embedding size 64, vocab size 1,000 or 50,000. So that's a really large vector. But in the past, when people did natural language processing, imagine the whole transformer would have been vectors of 1,000 or 50,000. That's crazy, and it would never work. Instead, those were called sparse and very large vectors because it was mostly zeros and then a 1 for the word that was active. So, who wants to look at all these zeros, right? And that was changed. That was like people hated this. And so they changed it to no, we need smaller vectors that are dense of 256 or whatever it is. And that's why embeddings are so much better. So now if you look from 64 to 1,000, and then I just run this one through it, another projection or matrix multiplication, and boom. Notice I called it my logits. Why logits? Because I have yet to run it through the softmax to become a probability distribution, which means it would add up to 1. That's very important, right? That it should add up to 1. And so here we can probably see the dimension. And boom, 2 by 10 by 1,000. But it's going to be values where one of them is going to be 0.98 and the other ones are going to be 0.0001 in a perfect world. So it'll pick the ID that is 0.98 and maybe that's 17. When you look it up with tick token, cat. Do you guys see that? All right, so go ahead. There's 2 sentences, you're right. You have 10 tokens in each sentence. Every token has a vector of 1,000. So for every one of those 10 tokens, there's a vector of 1,000. So it's gonna pick from that vector of 1,000 the highest value, and that becomes the ID for that token. Yes, 2 full sentences of size 10, and every one of those positions in 10 has a vector of 1,000 with a probability distribution that adds up to 1. The highest one of those is your ID. Yeah. You are getting 2 sentences, yes, of size 10 each. Yes, correct. That's it. We've completed a transformer, a GPT, from beginning to end. That's the whole thing. Obviously, the thing that I skipped is I don't have multi-heads. I only have one head. I didn't have multiple blocks, and we haven't done the training part. That's what we're going to do next Thursday, and hopefully so we're just going to go over the Huck Finn GPT from beginning to end, and if time permits, we'll be done. All right? All right, guys, so let's stop here for today.